Welcome, my beautiful people, to another episode from the Dino Basics. My name is Logan, and today we explore the basics on a time that, while distant, we still owe a great deal to today. From the vast fuel reserves we now pull from to warm our homes, to the advances in life that led to, well, us. A time where our ancestors first began to challenge the land, and a world where creepy crawlies reigned supreme. The Carboniferous period. The Carboniferous is a geological period which spanned from about 360 million years ago to 300 million years ago, around the middle of the Paleozoic era. The term was coined by geologists William Conybeare and William Phillips in 1822, based on the study of British rock and coal beds. The name stems from Latin, including carbo for coal and ferro for carry or to bear, having the name directly translate to coal-bearing. This name was chosen for the vast amount of coal deposits that originate from this time period, largely owed to the abundance of plant life during this time in the form of dense forests and swamps. It is also believed as the continents began to form Pangaea around 335 million years ago, this continental movement would bury a large amount of this plant material at the ideal levels of heat and pressure, resulting in the formation of these namesake coal deposits. The period is often divided into additional sub-periods and ages, but to not make this video any more complex than it needs to be, if you've been with this channel a while, you probably already know what you're getting yourself into. We will try to explore this period in a fairly linear format, and refer to the time as strictly Carboniferous, jumping between sub-periods and ages as need be. Cool? Cool. The Carboniferous would mark the end of the Devonian period, almost 360 million years ago. Around this time, the planet was still covered in vast oceans and largely composed of two large continents. Laurasia, the northern continent composed of North America, Europe, Greenland, and some parts of Asia, as well as Gondwana, made up of South America, Africa, Australia, Antarctica, and some southern areas of Asia like China and India. The land by this time had seen an explosion of plant life, with entire forests beginning to form composed of horsetails, ferns, and tree-like lycopsids, covering the tropical land masses in swamps and forests. Despite this diverse plant life, terrestrial animals were still fairly limited. Insects and other small arthropods seemed to be the most abundant life on land, including bizarre little creatures like the Strudiella devonica. Vertebrates around this time were only just beginning to flirt with the idea of land dwelling, such as the lobe-finned fish, Tiktaalik. This 9-foot or 3-meter long creature would sport a variety of structures, making them better adapted to moving onto land, such as sturdy interior bones in their fins, allowing them to prop themselves up onto dry land, similar to modern-day lungfish, as well as a more robust rib cage, possibly housing an early form of air-breathing lungs, providing them the ability to breathe outside of the water. While Tiktaalik and other members of its family were seemingly able to spend some amount of time on land, their inclusion of gills and still comparatively underdeveloped limbs indicated they would still spend a majority of their lives in the water. Invertebrate and vertebrate life around this time was still largely condensed in the oceans. Massive coral reefs had created vibrant ecosystems composed of invertebrates like the many species of trilobites, armored arthropods which had thrived for almost 270 million years up to this point. A variety of other invertebrates would also be native to these coral reefs, including brachiopods, ammonites, and other small shellfish. As for vertebrates, armored fish called plagoderms were also common during this time, including the 20-foot or 6-meter long Dunkleosteus, a massive predator often considered the first vertebrate apex predator. A variety of other sharks, rays, and fish would also thrive in the warm oceans around the continents. While these coastal reefs would provide a sanctuary for life, their oncoming destruction would pose a threat to many of these species. The late Devonian extinction is often considered one of the big 5 extinction events in our Earth's history, and hit the oceans of the ancient Devonian the hardest. Nearly 40% of all marine species would go extinct, with the sponges and tabulate corals that comprise these expansive reefs seeing a significant drop throughout this event. Many reefs would take hundreds of millions of years to recover, and the animals that relied on these reefs for food and safety, like trilobites, ammonites, and some species of bony fish, would take a significant hit. Exactly why this extinction occurred is not well known, with many experts providing a variety of possible answers, such as global cooling, increased volcanic activity, or possibly an impact event from an asteroid. One of the more interesting theories was a noted influx of nutrients into waterways, a process called eutrophication, which would lead into anoxia, or the absence of oxygen in the water. This is most easily seen in what's called algal blooms, where nutrient-rich water would see an explosion of algae to deprive bodies of water of oxygen, and thus killing off much of the fish and plants living in these waterways. But why would there be such an influx of nutrients? Well, remember these forests I mentioned before? The tall tree-like plants native to this time period, like a variety of species from the lycopod grouping, would need deep roots to gather nutrients and anchor themselves. These deep roots would break apart bedrock and create deep layers of topsoil. And topsoil, as opposed to clay or bedrock, is more prone to weathering and erosion. So as these forests continue to expand on land, the amount of topsoil on the Earth's surface would increase, and thus result in greater amounts of soil and nutrients flowing into waterways and eventually destabilizing the fragile warm ocean ecosystems so many ocean creatures relied on. In a roundabout way, for life to rise on land, the oceans they came from had to fall. It's almost tragic, until you think about what died and you say, you know what? I'm kinda glad you're dead. Unfortunately, our knowledge on the early Carboniferous period is limited due to a significant lack of fossil representation from about 360 million to 335 million years ago, nearly half of the entire period. This occurrence is often referred to as Roemer's Gap, named after American paleontologist Alfred Roemer, who first recognized this gap in 1956. Exactly why this gap occurred is not well understood, with some arguing unideal fossilization conditions and others arguing perhaps this is not a coincidental gap in fossils, but instead a reflection of a major drop in biodiversity brought on by the end Devonian extinction. Whichever the case, by the mid-Carboniferous, our planet was a drastically different place. The oceans covering our planet had seemingly recovered from the drastic loss of life brought on by the previous extinction event. Certain genera, like trilobites and bony fish, would not recover as well and would instead continue to decline throughout the Carboniferous. But many other fish species, like the elasmobranchs, including sharks and rays, would diversify and fill the niche as some of the largest predatory ocean creatures. Many species would take on bizarre shapes to specialize in different prey and lifestyles. Like the Stethacanthus, which would support a brush-like structure just above their spine, or the Ornithoprion, which resembled a discount swordfish with a long, sharp structure on their bottom jaw. A variety of other bizarre fish would fill these oceans, like the peculiar Iniopteryx, a small cartilaginous fish that would sport wing-like structures for fins, possibly hinting at a lifestyle similar to modern flying fish. Or the nightmare fuel that are eugenodontiforms, another group of cartilaginous fish that could grow up to 22 feet or 7 meters in length and sported curved, bladed teeth, often growing into perplexing jaw shapes. While the oceans had become a nearly unrecognizable place over a matter of 30 million years, further inland, many freshwater bodies would boast a similarly unique array of new life. A variety of freshwater fish would swim through the bog-like ecosystems and winding rivers, but the invertebrates who would call these waters home were much more eye-catching. Many of these arthropods, such as the 20-inch or half-a-meter-long megaarachne, likely lived an amphibious lifestyle, preying on fish and smaller invertebrates while still being capable of climbing onto dry land to rest or avoid predators. But for the invertebrates that chose to commit to the land, they would take on much more different forms, and much larger forms. Fossil records indicate the earliest terrestrial arthropods, like insects and millipedes, first appeared on land between 420 and 400 million years ago, and measured only a few millimeters in length. But by the mid-Carboniferous, they had grown to be some of the largest terrestrial animals on the planet. Many scientists believe this increased size was due to the increased oxygen levels of the time, with the atmosphere being composed of nearly 30% oxygen, compared to what it is today, at about 21%. These larger bodies have been proposed as a direct response to this increased abundance of oxygen. As opposed to many terrestrial animals like humans, who breathe using their lungs to suck in air from their mouth and nose, arthropods utilize a network of tubes called tracheae, which pull in air from openings across their bodies called spiracles. This system reduces the need for a more extensive circulatory system, and permitted insects to grow larger alongside the rising oxygen levels. It has also been proposed that this increased size could protect their young from oxygen poisoning, as certain studies have indicated that some insect larvae are susceptible to high oxygen levels, and since insect larvae breathe through their skin, they would have no way to regulate how much oxygen they take in. The larger bodies of arthropods, and in turn for their young, could potentially help balance out this issue, as increased body size would mean proportional to their bodies, the larvae would not be taking in as much oxygen relative to their size, and thus could avoid possible oxygen poisoning. To see just how big these bugs could get, look no further than the largest terrestrial invertebrate of all time, the 6.5 foot or 2 meter long Arthropleura. This mega millipede would have roamed what is now Europe and North America, and would have stalked through the dense forest floor, searching for food. Its enormous size and tough exoskeleton likely made it immune to many predators, but despite its foreboding appearance, this creature was likely a gentle herbivore, rummaging for decaying leaves and tree bark. But not all these giant bugs were necessarily gentle plant eaters. Take for example the Pulmonoscorpius, a 2 foot or half a meter long scorpion that would prowl through the ancient forests of the Carboniferous. This creature would sport many features similar to their modern day counterparts, such as grasping pinchers for holding down their prey, as well as a long tail ending in a venomous stinger, likely to neutralize or even kill the vertebrates and invertebrates it would hunt. Despite these similarities, it is believed Pulmonoscorpius would not have had a burrowing lifestyle as opposed to many of their modern counterparts, and was more likely active during the day as opposed to the nocturnal hunting style of many modern scorpions. But the ground was not the only place these arthropods had expanded to, as you merely had to look up to see the giant dragonfly-like Meganeura. This creature would sport a wingspan of nearly 2.5 feet, or 75 centimeters in length, comparable to that of a modern-day seagull. How these insects first evolved flight is not well known, but it is believed the structures that would evolve into wings were first used as thermal regulation tools for early insects. And by the mid-Carboniferous, insects would become the first animals to take flight and dominate both the land and the air. Scientists believe Meganeura would fly over bodies of water and swoop down like hawks to grab fish, insects, and small vertebrates before returning to the water's edge to feast on their meals. While insects had grown to become some of the most dominant animals on land, by the mid-Carboniferous, they were no longer alone. A new group of animals were beginning to take up permanent residence on land: the tetrapods. Tetrapods, or more simply four-limbed vertebrates, first began to appear near the end of the Devonian, such as our slimy salamander-like friend, the Tiktaalik. But throughout the early to mid-Carboniferous, tetrapods had seen an explosion in diversity, with many adapting in a variety of ways to take on a wide range of ecological niches. Some, like the stem tetrapod Crassigyrinus, would still retain a largely aquatic lifestyle. Reaching about 6 feet or 2 meters at full length, this creature was well adapted for hunting fish and aquatic invertebrates, with their eel-like bodies perfect for gliding through waterways, and their unusually large jaws lined with 2 rows of teeth, well adapted for crushing the tough bodies of their target prey. Meanwhile, their underdeveloped limbs, while more reminiscent of land-dwelling tetrapods than their lobe-finned fish ancestors, likely had limited use on land. In comparison, other tetrapods like the Pedipes seem more accustomed to land traversal. Measuring only about 3 feet or a meter in length, Pedipes had much more well-developed limbs that faced forward rather than sideways, indicating it was much more likely to move over land on a more regular basis. Based on the construction of the skull, it is also believed Pedipes would have air move directly into their lungs through a muscular action, similar to many tetrapods like birds and mammals today, and opposed to modern amphibians who would use a throat pouch to pump oxygen into their lungs. While tetrapods like Pedipes were certainly more well adapted for terrestrial life than their lobe-finned ancestors, these creatures were still semi-aquatic at best, relying on the water for hunting and reproducing. Their soft, moist skin also made them susceptible to prolonged exposure to the open air, drying out their bodies and forcing these creatures to return to the water to refresh themselves. However, a new classification of tetrapods would seek to more permanently remove themselves from the water: the reptiles. The oldest known reptile, which will provide a good point of comparison from their more amphibious ancestors, is the Hylonomus lieli, a small lizard-like creature that first appeared almost 320 million years ago. This 8-inch or 20 centimeter long critter was an insectivore, preying on small insects and millipedes. To allow them to hunt on land longer, Hylonomus had evolved scaly skin that did not require as much moisture as some of their more amphibious ancestors. But many amphibious tetrapods were not just limited by their own bodies. Many predecessors would rely on the water to lay their eggs, as the soft eggs, likely similar to modern frogs, would easily dry out on land, and their thin lining made them susceptible to physical trauma. To truly depart from the water, Hylonomus would be the first animal on land to acquire an incredible adaptation: the amniotic egg. Today, we often take these hard-shelled eggs for granted, just cracking them open and discarding their shells like trash. But in the Carboniferous, this new egg structure was a breakthrough in terrestrial evolution. Early tetrapod eggs were reliant on water to provide moisture and cushioning to the susceptible young, using only a thin membrane to house the growing embryo. The development of an amniotic sac served a similar purpose to the water, while the tough keratinous shell would provide structure to the amniotic fluid, and also protect the embryo from the dry outside world. This new egg structure, alongside the multitude of other adaptations, allowed Hylonomus to move further from the water, and better avoid aquatic predators, as well as reach food sources inaccessible to their water-bound competitors. Descendants of Hylonomus would continue to expand on these traits over the next few million years, such as the Archaeothyreus, which first appeared 306 million years ago, and would develop a single fenestra, or skull opening, towards the back of their skulls. Despite its very lizard-like appearance, it is actually the first known example of a synapsid, a classification of animals that would eventually become mammals, including humans like you and me. While around the same time, the similarly sized Petrolacosaurus would develop their skulls to include two openings near the rear of their skull, to become the first example of a diapsid, the most successful grouping of reptiles, which would go on to include many modern snakes and lizards, as well as the dinosaurs. Probably the longest I've gone in a video without mentioning them. While these were remarkable evolutionary steps for terrestrial tetrapods, this classification would remain considerably smaller than their arthropod neighbors and amphibious relatives. The warm, humid climate of the mid-Carboniferous provided the perfect conditions for these jungle-like forests to thrive, and provided the ideal ecosystems for these big boys to continue to dominate. It would take something like intense glaciation to drop sea levels and create a less hot and humid climate and replace it with a cool and arid one, which would lead to a collapse in rainforest ecosystem these animals relied on. So about 305 million years ago, the Carboniferous rainforest collapse occurred. Many of the giant lycopsids and seed-bearing ferns that comprise these dense forests took a significant hit and posed a direct threat to the wildlife that relied on them for food. Despite how dramatic the name sounds, this extinction event is often considered a fairly minor one in the grand history of extinctions. And this shifting climate likely did not eliminate all of these forest ecosystems. Instead, it likely reduced their sizes and split forests into smaller ecological islands for the native fauna to continue to survive, just restricted to much more limited territory. While you would assume the giant arthropods would be hit the worst, with this loss of habitat as well as the lowering oxygen levels from these reduced forests, recent studies actually indicate some of the largest arthropods, like Arthropleura and Meganeura, would continue to survive after the extinction event, indicating this collapse was not as immediate on arthropods as opposed to something as dramatic as the asteroid and the dinosaurs. These giant arthropods would gradually die off, moving into the early Permian, but this extinction event was likely only a single factor, with other factors like increased competition from tetrapods and greater predation likely leading into these giants' decline. One group that was more dramatically hit by this extinction were amphibians. These drier and colder climates were not ideal for large or small amphibious tetrapods, and many groups would die off moving into the next geological time period, unable to compete in these new ecosystems. Some amphibians would continue to persevere and have their descendants evolve into modern amphibians, like salamanders and frogs. But amphibians would never reach the same level of dominance or diversity they would achieve in the Carboniferous. After all, this was a much different world. By the end of the Carboniferous, the continents of Laurasia and Gondwana had been well underway in creating the new megacontinent of Pangaea. Sea levels, oxygen levels, and climate temperatures were gradually dropping, bringing an end to the conditions that defined the Carboniferous for 60 million years. With the end of this dynasty, a new group of land dwellers would seek to fill the void on land. The amniotic tetrapods, with their scaled skin, uniquely adapted eggs, and more well-developed limbs, were perfectly equipped to dominate these new conditions on land. The diapsids would continue to evolve throughout the Permian, but they were still a long way from growing to the giant dinosaurs they would one day become. Instead, they would be overshadowed by their amniotic cousins. The age of amphibians and giant insects was now over, and the Permian period, the age of the synapsids, had begun. That's gonna do it for this episode. Thank you so much for watching, and I hope you enjoyed. I personally wouldn't mind doing another granular look at a geological period like this. It lets me talk more about trends more than just hyperfixating on one creature. So leave a comment below what time period you would want to see analyzed more closely. But next week we are hyperfixating on one creature, as we take a look at the false ceratosaur, Proceratosaurus. Thank you for your support, and see you in the next video.